Greetings from Easy BTech. I'm Dr. Gayatri. Hope you could recall me. In the last topic of energy, wave function, eigenvalues, and eigenwave functions of a particle inside one dimensional box, we have calculated with eigenvalues. Now have a look at eigenwave functions. How to determine this eigenwave functions. So if we could recall in the last topic when we were learning with this eigenwave functions, we assumed that an electron is trapped inside a metal box whose length was considered to be A. The dimension here, the length was considered to be A, and the height of the box was infinite. So we are calling it as an infinite potential well. Or else we can also say here that consider a metal whose length is A. Now, an electron which is trapped inside this metal box is considered. When the electron is trapped inside this metal or one dimensional potential box, its potential is assumed to be constant. For time being and simplicity, we are saying that this potential is equal to 0 when electron is within this box. Outside this box, we doesn't know the potential here, so it is considered infinity. Here you are having its potential to be infinity. So we have here the conditions to be V of x to be 0 when electron is within this length in the dimension of the box. So I can write here for 0 less than or equal to x less than or equal to a. But when the particle is outside, we doesn't know its potential, which is nothing but infinity. So v of x equal to infinity for x less than or equal to 0 and x greater than or equal to a. That means when the particle is greater than this length a, x greater than or equal to a, potential is infinity, and when the particle is outside the box, v of x is equal to infinity for x less than or equal to 0. Now recall with our time independent Schrodinger equation wherein we said that dou square psi by dou x square plus 2m by h cross square e minus v psi of x equal to 0. Here we know that this is a second order time independent second order differential equation in the variable psi where the psi is a wave function. So we are having this wave function psi of x to be written as a sine kx. Already while calculating eigenvalue we have seen that this k value is given as n pi by L. Now under this wave function, let us determine this constant a value. So to calculate this constant a value, we are going to recall the normalization condition. So what is a normalization condition? Generally what we have learned is under normalization condition, integral 0 to infinity psi, the wave function, its conjugate psi star, or I can also write it as mod psi square into dx equal to 1. This is the normalization condition. So we are recalling with our normalization condition here. Normalization condition. So now what does this psi stand for? This is nothing but a sine kx. So substitute the same thing here and proceed further. And since you are having here electron to be within the box whose dimension is considered as 0 to a, my limits will change from 0 to a. Integral 0 to a mod psi square, that is psi star means mod psi square. So I can write this equation as a square sine square kx dx equal to 1. Now it's the time for integration. Just recall with your integration formula for your integral a square sine square kx. So how do we integrate this equation? First take your constant out of integral. Then we need to have the sine square kx to be expressed in a different way. So please don't get confused here. It is not expressing as 1 minus cos square. It is 1 minus cos 2kx divided wholly by 2 into dx equal to 1. Our limits here are 0 to a. So how did we write with the sine square kx? It is mentioned as 1 minus cos k2kx divided by 2. Now it is easy for us to have integration. With sine square kx, it is only an iterative function wherein you do not have any break for your integral value. So we are expressing it as 1 minus cos 2kx. This is the most important step here where generally people will make mistake. So I have here a square by 2 1 minus cos 2kx. That means it is dx. What is the integral for dx? It becomes x. So coming for your cos 2kx, it is simply your form of having cos 2 theta. What is the integral value for cos 2 theta? Sin 2 theta by 2. Similarly, here cos 2 kx means I can write this as sin 2 kx divided by 2k. This is how we have integration to be done. It is a finite function with the limits as 0 to a, which is equal to 1. Now we have done with the integration. Now let's move on substituting the limits. We could observe here the upper limit is a. So I have here a square by 2. Upper limit taken as a minus sine 2ka divided by 2k. What is our lower limit? 0. So 0 minus sine 2k, x means here once again 0. So how much it becomes? Sine 0 means it is once again 0. 0 by 2k is 0. This is the lower limit. So you are having this to be equal to 1. Now if you look at this part, sine 2ka, we have already determined while calculating your eigenvalue energy that k is written as n pi by a. So use the substitution k equal to n pi by a. So let's look at this value first. Sine 2, instead of k I have n pi by a into a. So what will happen? This a is simplified. So you will be left with sine 2 n pi. What is the value for sine 2 n pi? Just recall. Sine 2 n pi, that is simply 0. So what happens for the sine 2 ka? This is going to become 0. 0 by 2k will be 0. So then what is left for us? A square by 2 into a equal to 1. So from this expression, you can write here a is equal to square root of this a taken onto the other side comes to the denominator, and this 2 whatever you are having will be taken to the numerator. So you have a small correction here. You are having a, capital A, the constant, equal to this 2 taken onto the other side becomes 2 in the numerator and a comes towards denominator. Instead of square, while taken onto the other side, it becomes square root. So you have here a is equal to root of 2 pi a. So what is happening for your wave function now? Your wave function was psi of x is equal to a sine kx, where a is a constant. Now we observe that this constant is root of 2 by a into sine kx. Therefore, this represents for you the expression for normalized wave function, or I can say this as normalized eigen wave function of the particle. This is a normalized eigen wave function of the particle which is trapped inside the potential box, whose dimension we have considered here as A. So let's look at the first three normalized wave functions, how we could represent. Psi 1 is the first normalized wave function, psi 2 and second one, and psi 3 is third one. So when I have here, these are the wave functions, corresponding probability densities are given as mod psi 1 square, because it is psi star, the conjugate function. For psi 2 it becomes mod psi 2 square, and for psi 3 it becomes mod psi 3 square. Now if we plot here the graphs for this, when the particle is inside the box, the dimension was taken as A. So it becomes x0 to A. Here you know that sine kx means n pi by A. So for n is equal to 1, it represents you with n equal to 1, the first one, which is psi 1. If I go for the next, n is equal to 2, it has a positive and a negative. This is n equal to 2, which is psi 2. If I go for the next stage, this is n equal to 3. Then I have n equal to 3, which represents the third one. Normalized conditions can be now represented in this way. The probability density functions. Your probability density function is the square of the wave function. So I will have here the first one to be psi 1 square with the mod, which represents you positive value for n equal to 1. If I do with second one, you are having psi 2, a positive function. This negative function on squaring, this also becomes your positive function. This is your mod psi 2 square. This is for n equal to 2 and this is for n equal to 1. Similarly, if I go for my third one, if I look at for third one, this becomes mod psi 3 square for n equal to 3. These are how we are having the three graphs to be represented. So the eigenvalues and the corresponding wave functions have been done. Thank you.